In this video, I want to talk about how we can actually go about and do inference in maximum likelihood. Because at the moment, we've talked about how we can actually derive the maximum likelihood estimators for the parameters, but we haven't actually talked about how we can actually go ahead and do inference. And in order to do that, we're going to define a concept which is known as the Cramer-Rao Lower bound. Okay, so if it is the case that we have an unbiased estimator, in other words, the expectation of our estimator theta hat is equal to the true population parameter theta, then it is possible to show for any estimator that the variance of our estimator theta hat is always greater than or equal to something which is known as the Cramer-Rao lower bound. In general, for maximum likelihood estimators, they're not in general unbiased. So we're going to have that the expectation of theta hat maximum likelihood in general does not equal the true population parameter theta. And what in turn this normally proves is that the variance of theta hat maximum likelihood in these circumstances is greater than the Cramer-Rao lower bound. Okay, so what is this Cramer-Rao lower bound? Because it's something which I've just sort of brought in out of the blue. Well, it turns out we can define it in terms of something else which we also don't know, which we'll then come on to define. But the Cramer-Rao lower bound is defined as in terms of something which we call the information matrix for a parameter vector theta, which I'm going to write I of theta. And it confusingly isn't actually the information matrix, it's actually the inverse of the information matrix. Okay, so what is this information matrix? It just seems like I've replaced something else which we didn't know with something else which we also don't know. Well, it turns out that we can actually write out this matrix here, I of theta, where note here that we're talking about estimating a parameter vector, so a range of parameters rather than just one particular parameter. And because of that, we're going to get out a information matrix. So the information matrix is defined as being equal to minus the expectation of the second differential of the log likelihood, which is that which we defined in previous videos, with respect to the parameter vector theta, and then the transpose of the parameter vector. So if we're talking about estimating one particular parameter, or there's one particular parameter in our model, the information matrix will in those circumstances be a scalar. But in general, we're going to be talking about how we estimate a parameter vector, which is going to mean that the information matrix itself is actually a matrix. Okay, so how does this information matrix help us in terms of maximum likelihood inference? Well, it turns out that because of the fact that maximum likelihood estimators are themselves asymptotically unbiased, in other words, they are consistent under a range of conditions, then the parameter vector, or the parameter estimator rather, of the parameter vector, which I'm going to write theta hat maximum likelihood, tends in probability towards the true population parameter vector theta. And because of this, we can actually invoke the central limit theorem, which says that the sample size to the power half times our parameter vector, or our estimator for the parameter vector rather, theta hat ml minus theta, is going to tend in distribution to that which is normal, which is centered around 0, so it's asymptotically unbiased, and it's going to have some variance which I'm going to call h of theta. And note that we've got a matrix here for the variance because of the fact that we're talking about particular covariances between some of the estimators as well. And what this then goes on to, what we can then use this for rather, is we can use it to sort of derive an asymptotic distribution for theta hat maximum likelihood. Or in other words, we can derive a sort of approximate distribution for large samples for theta hat maximum likelihood. Because technically, I shouldn't really be dividing through by this n to the half here, but if we do that, we're going to get that theta hat maximum likelihood is going to tend, it's not going to be tending in distribution because it's actually at the sort of limit when the population size is infinite, there is no variance at all in theta hat maximum likelihood. But we write an A here to mean that it's approximately tending or asymptotically tending towards a normal distribution which is centered around the true population parameter vector theta, with a variance which is given by the information matrix, or the inverse of the information matrix rather. So this information matrix, or rather the inverse of the information matrix, actually defines a good approximation for the asymptotic variance of theta hat maximum likelihood. And because of that, we can actually use the information matrix in order to do inference in maximum likelihood situations.